Welcome to Chapter 1, Part 3, Sections 1.5 to 1.8. We will now discuss three-dimensional basis vectors, unit cells, and lattice transformations. The unit cell, in the last program, we discussed the two-dimensional case, which is a parallelogram defined by basis vectors A and B, and now our unit cell will be a parallelepiped defined by basis vectors A, B, and C. As in two dimensions, the unit cell fills space under translation. The definition of a lattice remains the same as two-dimensional. It's an array of points in a crystal with identical neighborhoods. The array is defined by the translation vector T, which is a linear combination of the basis vectors A, B, and C, where the coefficients are integers running from minus infinity to plus infinity to give us the primitive cell. The three-dimensional basis vectors can also be done as A, B, and C, alpha, beta, gamma, and the definition of gamma is the angle between A and B. Here is gamma, and the definition of the angle between B and C is alpha. So let's have your question to ponder. What is the angle between vector A, and vector C? So that's this vector between A and C. We have A, alpha, gamma, and the one we're looking for. Yes, you've guessed it correctly. It is beta. So here I've put in beta over here as well as the answer. Here is the three-dimensional lattice with all the unit cells piled up. And now we have to consider a conversion to Cartesian coordinates. The reason we need to do the conversion to Cartesian coordinates is so that the computer can draw out graphics. The computer doesn't work in terms of basis vectors A, B, and C, which are not necessarily orthonormal, but the computer does use an orthonormal set. So we need a conversion from the basis vectors A, B, C to the computer vectors, the orthonormals, E1, E2, and E3, and that matrix we're going to call C, stands for conversion to Cartesian. So here in two dimensions, we'll start out with E1 and E2. We'll lay the vector A. The easiest place to put it is on top of E1. So we can write out A runs along in exactly the same direction as E1, but has a different length. That length is going to be italic A, which is the scalar A, the length of the basis vector along A. Now the next thing we're going to do is the vector along B, and we'll have a question to ponder, which is what is the vector B in terms of E1 and E2? So here's your B, and you have to look at the projections along E1 and E2. So there's our answer. So you can see that B is equal to B cosine gamma times E1, and B is equal to sine gamma times E2. Now we want to put these two equations into matrix form. So we always have our vectors along the rows, and so here we can write this E1, E2 in terms of these two equations will be this matrix C, and now we can put this in a little easier form. The translation, the lattice is going to be either the same information can be either in terms of the E1, E2, which is especially for the computer, or the A and B, which is especially for the crystal. We can write these two in this format, in the matrix format, as we've done before, this E1 times X and E2 times Y, which is this one, and similarly the one UA plus UV is written in this format. Notice again that the vectors are always in rows and the scalars are in columns. And now we can, this gives us a way of creating this matrix C, and now we can look and put it in a little bit different format. You have the AB is, we're going to substitute into this equation, this E1, E2 row vector times C, and when we do that, we have this, and then we've made this substitution in here. We get this equation, and you can see the E1 and E2 are both on the left side, so we can extract the X and Y equals C times U and V. That means if you start out with the lattice, which is the U and V scalars, and you operate the C matrix on top of that, you're going to get the components necessary to plot. That's what you're going to put into your MATLAB programs. For example, suppose we want to find the coordinates, the Cartesian coordinates of the point 41, the lattice point 41. We have the C matrix, and then we put the 41, which is the components, the scalars for that position, and then we can substitute in our C matrix. We multiply that out and get this form. So that shows that the computer plots 4a plus b cosine gamma as the x component. This is the x component, which you can see here is x, and then the y component is here, which is b sine gamma. So for the coordinates of the point 41, you can see that you have 4a, and then we have this projection along here for b cosine gamma, and then to go up we have to go b sine gamma. So that's exactly what we have over here. One of the exercises 1.6, and I'm just going to run through what you do here. I'm not going to actually do it for you, but you're looking for the transformation matrix P. Here are your three relationships between the 1 subscript and the 2 subscript, and you put them in a column, and you take the coefficients of 1, 2, and 3, and you lay that down the column, and you continue and create the P matrix. Now if you want to determine the handedness, if you start out with a right-handed system, you're going to take the determinant of P, and if it's equal to a positive, then the new set is going to be right-handed. If it's negative, the new set is going to be left-handed, and if it's 0, you have you do not have your vector, your new transformation is not possible because it's nonlinear. It's 0. So the demonstration that the new vectors are linearly independent, you show that by showing that the determinant of P is not equal to 0. And then if you want the ratio of the number of lattice points in the new set relative to the number in the old set, as in 2 dimensions, the number that you get for the determinant is exactly that ratio of the lattice points in the 2 cells. So now we can go to 3 dimensions, and we have A, B, and we haven't done C yet, so we can write C in the general form. It perhaps has a C1 component, perhaps as a C2 component. It certainly will have a C3 component if it's going to be linearly independent. And we make use of some of these identities, namely in the orthonormal system, if the indices are different, the angle between E1 and E2 is going to be 90 degrees, E2 and E3 is also 90 degrees, and 1 and 3 is also 90 degrees. The cosine, which is the dot product, is going to be 0. Therefore, all of those dot products are going to be equal to 0. On the other hand, if you take a vector into itself, the angle between the vector and itself is 0, and the cosine of 0 is going to be 1. So since these vectors all have a scalar of 1, then this is true. E1 dot E1 is going to be 1, and similarly for E2 dot E2 and E3 dot E3. Now with this in mind, we can calculate what C1 and C2 are by taking the dot product of A with C and then B with C. So if you take the dot product of A with C, we know in general that means that we have A, C, and then the angle between them, which is cosine beta, as you've seen from the previous slide. And on the other side of the equation, we have the dot product between E1 and E1, and then E1 and E2 and E3. These will drop out, they'll be 0. So the only thing that's left is going to be this BC1. So, I'm sorry, AC1. And here we have it, this is the AC1. So we have C1 here, and you can see that the A's, if you compare these two parts of the equation, the A is non-zero, so we can drop that. So we have C cosine beta, which is over here, is equal to C1. And here's my C1 over there. So we've now solved for C1. We do a similar situation to get C2, which is we take the dot product of A and B, and I've written it out here, and you can follow that along. And when you do that, you'll get C2 is equal to this expression here, a little bit more complicated. And now we need to get C3. We already have C1 and C2, and we get C3 because we know that if you take, since these are orthonormal, if you want the scalar value of C, we take C1 squared plus C2 squared plus C3 squared and take the square root of that. We'll get C squared, and we can solve that for C3. We bring this over here and we get C3 is equal to C squared minus C1 squared and C2 squared, both of which you know. We have the square root. The square root can be either plus or minus. If you choose the square root as plus, you'll get a right-handed system. If you choose it as minus, you'll get a left-handed system. And in crystallography, we always choose the right-handed system, so it will be a positive. And then when you substitute C2 and C1 into that equation, that's the full equation that you get. So the transformation, the C matrix in 3 dimensions, is just this form here. And when you program it, put the C1, C2, and C3 like this, and then enter above the C, always enter in the C1, C2, and C3 in separate lines so that you can, if you've made a mistake in your entry, you can catch that. Now you have this translation. It's equal to, you can set this up so that the E1, E2, and E3s are similar to what we had before. And if you run through that same argument, you'll get that the column vector, which is the scalar, is equal to C times the lattice, the indices, and that will take us from the crystal world to the world of the computer, which is the X, Y, and Z. Now let's look at a real example. One of them is hexamethylbenzene. We have a benzene ring here which has 6 carbons in it, And then on each carbon is a methyl group. The methyl group consists of a carbon and 3 hydrogens. This is not a chemistry course, so we will tell you all of this type of information. And all of these red circles are carbons, and they are all lying in a plane. The hydrogens poke out of the plane, and so you can see that's what the molecule looks like. Now we need to proceed, we need to define angstroms. So we have 1 angstrom is equal to 10 to the minus 10th meters, or a tenth of a nanometer, or 10 to the minus 8 centimeters. And here are the lattice parameters for hexamethylbenzene. You can see that A, B, and C are roughly 9, 8, 9, almost 9, and 5. And the angles between them are 44 for alpha, 116 for beta, and 119 for gamma. These were observed or experimentally observed by Kathleen Lonsdale in 1929. So now we can do our 2-dimensional cell for hexamethylbenzene. You'll use a starter program to create this 2-dimensional cell, and then the 3-dimensional cell, you'll just start out with the starter program and just adjust it for your crystal. This is not a computer course, that's why we write all the computer programs for you. But we want you to basically understand this. We'll be using this C matrix, and then in the computer world we can put all of these lattice points conveniently as columns. So here's the 0, 0 is here, here's the 1, 0 is over here, and the program is written such that you go from this point to this point to this point, and here's the 1, 1 up here, and the 0, 1 over there, and we're back to 0, 0 over here. And then when the computer will, of course, do all this multiplication out, and it will trace that. Now this is what the computer program looks like. You always have a purpose to your program. You always start with these 3 little words, CLC, close all, and clear. That's so you don't get mixed up with a previous entry into your MATLAB. And you'll always put this line here, you'll put a new line in, you'll put the date that you're working on it, you'll put your name here, and then you will put adjust code for problem so-and-so, or whatever you're doing. We're defining our variables A, B, and gamma, and now we write them out. Here's our A, B, and gamma as are in the previous slide, and here's my conversion to Cartesian. Here's my outline of the cell, and in this particular case I've only started at the origin and I've come up to A, and so I'm only giving you 2 points, and then what you're supposed to do is just put in the rest of these points. There's also a little video that describes this more in detail. Then you will plot the points, and this shows that you've already gone through the conversion and the Cartesian conversion. And these entries allow you to control the line width, for example, and the color, etc. And the axes equal, you need to have that in to preserve the relative lengths of the axes. We don't want the axes drawn in because we want it to be pretty. And we have a hold on, which allows you to not start a new figure. So the hold on, we'll use it to label the axis, and here's the B axis, and here's the A axis labeled boldface A. And when you run the starter program, you're going to get the A, and the arrow is put on here, and you'll get the B, and you have to finish it so it looks like the A and the B, and you go around the loop to show the 2-dimensional cell. The next thing we need to do is to look at the 3-dimensional cell for hexamethylbenzene. And so your next problem will be to take that previous program and up it to 3 dimensions. So you'll have, instead of XY, you'll have XYZ, and instead of UV, you're going to have UVW. So, and when you trace the figure, you can trace it, say, coming like this. You don't want to take your finger, so to speak, your computer off the. It has to be continuous. Now you come back over here, and now you can say do this side. You can just select what you want. Now you've already drawn this line in, but the computer will allow you to draw it over and over. It doesn't really matter. You can just keep going until you complete the whole diagram. You can go back over lines and it does not show. So this is the way it's going to start out to look. We need to have the conversion has to be three-dimensional, and then of course all the entries will be three-dimensional as well. And you can follow that out as 0, 0, 0, 1, 0, 1, 0, 0, and this one is up to 101, etc. And finally, we have another crystal altogether, anhydrous alum. This is a framework structure, potassium aluminum disulfate. And here's the lattice parameters. And once you already have the program, all you have to do is put in A, B, C, alpha, beta, gamma, and all the rest is done for you. You have to, of course, change the purpose of your program is to produce, say, another cell anhydrous alum. Then what you're going to do is you're going to take your own personal crystal, which will be for the Festival of Crystals, and you will put that into the program and create your own unit cell. That's all for now, guys. Talk to you later. Bye.